Okay, hello everybody. Good morning, all of you. So we'll start with today's quote. The harder you work for something, the greater you will feel when you achieve it. So the more you struggle for something, the more you will be happy when you get it. Anything which you get free will not have real happiness in getting it. But if you struggle for it, then you will see the happiness out of it. Okay, some time back I heard a story. One father asks his son to work hard and get something. Okay, so I will give you my uh, assets only if I see that you work hard and get something out of it. So what he does is he will go to his mummy and get some money, and at the end of the day he will come and this is the thing I have earned. And so the father immediately he tears off that money, whatever he gets it. And that fellow gets upset and goes, and he says, now you work and come back. And he goes and gets money from some friend. So again, he will do that. And that again, he will ask, again, no, work hard and get it. And then like this, it happens three to four times. And then finally, he will go and work hard outside. So physical work he will do and get some money and bring it. And again the father will tear it, and that fellow gets upset and he becomes angry, and what do you mean you are tearing away my hard work and all? Then the father says, now you have worked hard, that's why you are upset, right? So you can understand the thing, whatever you get out of it, your work, so that will give you the real happiness. And that's why many people, whoever gets the campus selection in the big campuses, normally they will not be happy with the job they get. Always either they shift or they complain or something like that. But the persons in private college, they struggle and work hard and get some job, even menial job, they will be very happy of it. Okay, the easier you get, you won't feel the worth of it. Okay, that's what just I wanted to say. Okay, today is the birthday of Robert Boyle. I think everybody is familiar, Boyle's law and all. So he is the person who born today. So he is Irish-English chemist and natural philosopher, noted for his pioneering experiments on the properties of gases and his espousal of corpuscular view of matter that was a forerunner of the modern theory of chemical elements. That is the particle nature of the elementary particles. Okay, he was a founding member of the Royal Society of London. From 1656 to 68, he resided at Oxford, where who helped him to construct the air pump. And with this invention, Boyle demonstrated the physical characteristics of air and the necessity of air for combustion, respiration, and the transmission of sound, published in New Experiments Physico-Mechanical Touching the Spring of the Air and Its Effects. So that is the book he has written. And in 1661, he reported to the Royal Society on the relationship of the volume of gases and pressure, which is we study as Boyle's law. And he says, God would not have made the universe as it is unless he intended us to understand it. So he made the universe in such a way that we can understand the universe. So that's what he says. Okay, today we discuss about finite difference formulations. Okay, I think I'm not getting the power into the board. I think whether I can write it on the... Okay, I think I have to depend on PPT only. Okay, Talos is expansion. Okay, I don't know the whiteboard, I think.
Click on the pen icon.
I think maybe pen battery, I think, is over. I have to change it. I purchased it, but I don't know where it is. Okay, I will manage like this only without that. Okay, as I told, we have partial differential equations, which are to be converted to algebraic equations, and then we solve it. And so there are three methods. We know it, like finite difference methods, finite volume methods, and finite element methods. Okay, I think one basic difference I have explained. What is the difference actually? Any difference you know among them? Or when is what is used and all? Because this is one important thing normally in interviews people may ask. Okay, finite difference method is differential approach which solve differential equations. And finite volume methods and finite element methods, they are integral approaches. They solve integral equations. And I think, I don't know whether I told you or not, out of differential equations and integral equations, people say integral equations are more fundamental. Why? Because, did I tell you about this?
Yes, sir.
Yes, sir. Discontinuity, right?
Discontinue.
Yeah, right. So differential equations, they need the functions to be continuous. Integral equations, it can be discontinuous. So we call the integral equations as fundamental. Okay, so that is one thing. Okay, so when you use finite difference methods, finite volume methods, and finite element methods, one finite difference methods is the simplest of all. Okay, so which we are going to study. The whenever there is something simple, but still why we go for other methods is there are some constraints. Okay, the main constraint is the geometry or the domain, flow domain. Flow domain must be a regular, like a rectangle like thing. If it is a Cartesian system, I have to have a rectangular domain. If it is a cylindrical system, I have to have cylindrical domain. Like standard domains only I need. Then only I can solve them. But finite volume and finite element methods, it can solve for any type of domain. Okay, why this restriction is finite difference methods, they need the grid lines confined to coordinate directions. Okay, so if I have Cartesian system, I will have Cartesian, that is rectangles only must be the grid, that is control volumes of these things. Okay, so I should have only horizontal lines and vertical lines. Then only I can do. So this is what is called a structured grid. Okay, finite difference method is confined to only structured grids. This is main important thing. And finite volume and finite element methods can be used with any type of grid. So because of that, I can have unstructured grid there. Okay, so unstructured grid, we can discretize any domain, any complex domain. Okay, any complex shape. There can be discontinuities in the shape also. Right? So when there are discontinuities in the shape, I cannot have rectangular domain, that is rectangular grids, but we can have triangular grid. So if I have triangular grid, I can have grid for any type of domain. There is no constraint for that. So that is the main advantage of finite volume and finite element methods. Okay, so that's why all the present day calculations and the packages are written for finite volume methods. Okay, what is the difference in finite volume and finite element methods? Finite element methods are well developed and mainly used in structural problems. Okay, then people are there who are using it for CFD also, but in the whole India, if you take one or two professors in IIT Madras or IIT Kanpur, some very few, you can number them in fingers, right? So only very few people are working with finite element method for computational fluid dynamics. Okay, one main restriction or constraint for finite element methods, I think that also I have discussed. As the size of the matrix or the number of grid points increase, the round of error will be very huge. Okay, that is one of the main restriction. And another restriction is linear equations, right? The finite element methods are best suited for linear equations. All structural problems, they are linear equations. That's why it is well suited for that. So here also, if you have only linear equation like Laplace's equation or Poisson equation, if you had to solve, so then finite element method can comfortably can be used. But when there is convection term, which is non-linear, finite element methods, they are quite inefficient. So the best suited one is finite volume methods, no restriction of linearity, no restriction of structured grid, no restriction on the type of domain, anything can be solved. So that's why all commercial packages, they use finite volume method only. Okay. And why we discuss finite differences? Okay, finite difference is initially developed and all these concepts are applied in finite volume method. It is like knowing C before knowing C++, something like that. You can directly learn C++ also, but if you know C, C++ will be comfortable, only some additions are there. But the basic concepts for finite difference and finite volume method are same. Okay, so whatever I say about consistency, whatever I say about stability, and whatever schemes I use here, similar schemes are used there. Only thing is conceptually a little bit difference will be there. Okay, so we concentrate on finite difference methods. Okay, that is one of the main thing. So here for discretization or conversion, this is called as discretization. Okay, finite volume, finite difference, finite element method, all are called discretization methods. So when you come to finite difference methods, so I have to do what is called as finite difference formulation of partial differential equations. Finite difference equations are nothing but algebraic equations. Okay, for this, we have different schemes like Taylor series expansion method and polynomial method. Okay, these are the two methods we are going to learn. Taylor series method and polynomial expansion, using Taylor series expansion and polynomial expansion. So first we'll see using Taylor series expansion. Okay, can anybody tell me what is the use of a Taylor series?
We can convert non-linear to linear.
No.
Like we know the
We
differential
can find
equation,
the
but we don't know the exact solution of the differential equation. We can find the next. We can find the value of that equation at next
Okay,
step.
from the now here I have written the Taylor series expansion. Actually, what it gives.
if we want the value of a function at a later point, and we know the value of the function at a present point.
Yeah. If you want to have the value, or if you know the values and derivatives, value of the function and all its derivatives at a particular point, I can find out the values of the function at neighboring points. If you know the value of the function and all its derivatives at a particular point on the curve, I can find out the values of the function at all the neighboring points. Am I clear?
Yes, sir.
So if I know f of x dou f by dou x, dou square f by dou x square, dou cube f by dou x cube, etc., all its derivatives, I can find out f of x plus delta x, the next point, f of x minus delta x at the previous point, or f of x plus 2 delta x, x plus 3 delta x. Like that, I can find out the value of the function at all the points. So that is the purpose of Taylor series expansion. That's what the expression says. But here, I try to do it in a reverse way. So knowing the values of the function at all the points, I want to find out the derivatives at a particular point. Am I clear? Because in partial differential equation, I have derivatives are there. First order derivative, second order derivative, third order derivative, like that. So I want the values of the derivatives in terms of the functions at that point and the neighboring points. Am I clear?
Yes, sir.
Yeah. So now this is the Taylor series expansion. All of you know it. F of x plus delta x is equal to f of x plus delta x dou f by dou x, delta x whole square by factorial to dou square f by dou x square, like that, etc. This is in finite series. Okay. And the point previous to it. So normally we write this as fi plus 1 is equal to fi plus delta x f dash I plus delta x whole square by 2 f double dash I. Actually, if I write it, I write in that way so that the writing will be easier. Okay, so that is the way. This is fi minus 1 is equal to fi minus delta x f dash I, delta x whole square by factorial to f double dash I, like that. So this is fi plus 2. Okay, that is next second point on the forward side. So this delta x is to be replaced by 2 delta x. Like that, I can write 3 delta x, 4 delta x, like that, and minus 2 delta x, minus 3 delta x, like that. I can get all the neighboring points on the forward side and also on the backward side. So that is the way I can write the values of the functions. Okay. So I told you now I want to get, using these values, I want to get the values of the derivatives. Okay, so how to do that? So if I take the first equation, if I want f dash I, that is f dash the dou f by dou x, so what should I do? Take this fx in this side, okay, and divide by delta x, f of x plus delta x minus fx by delta x. And all these terms I neglect. This is what is called as truncation error. I am neglecting the higher order terms. Okay, so that is truncating. So that is called as truncation error. So this is truncation error is the one which comes in the formulation itself. So you can take order of accuracy. Suppose now if I neglect all these points, because after dividing by delta x, I am neglecting them. So what is the biggest term here? This is the term, and delta x whole square by delta x means delta x only is the highest order here. This is delta x whole square. So bigger, because delta x is less than 1, this is the biggest error. So the order of accuracy is delta x. Am I clear? Anything, if you have doubt, you ask me. So dou f by dou x is equal to f of x plus delta x minus fx by delta x with first order accuracy. Order of delta x is the error. This is the error. This is order of delta x. In this is what is called as forward difference approximation. I am using the value of the function at fi plus 1, that is 1 forward. Using that, I am calculating the derivative. Okay, suppose this is I plus 1, I minus 1. So I am finding out the slope here in this way, but it can be taken this way, or it can be taking both the neighboring points. Okay, so if I take a point later to that, that is forward difference. And if I take a point before that, it is backward difference. If I take both the neighboring points, it is central difference. Okay, so if I take this second line, f of x minus delta x minus fx by delta x. If I take all these things to the other side, okay, so then fi, this if I bring this side and all these things to this side, fi minus 1 by delta x, again the error will be of the order of delta x. This is called as backward difference. You can see here, Dou f by dou x is fx plus delta x minus fx by delta x and order of delta x. And if you write in terms of suffixes, fi plus 1 minus fi by delta x, order of delta x. This is first order derivative with first order approximation or first order accuracy. So backward difference, fi minus 1 by delta x. Okay, again first order accuracy. But if I take central difference, means I take these two neighboring points, fi plus 1 and fi minus 1. Okay, what I do now, if I just subtract one from the other, okay, so fi plus 1 minus fi minus 1, this gets cancelled, right? So I get 2 delta x into dou f by dou x. So fi plus 1 minus fi minus 1 by 2 delta x gives me 2f by 2x. And this gets cancelled. Okay, so this gets cancelled and this by delta x is the error term. So that is second order accuracy I will get. So you can see here central difference fi plus 1 minus fi minus 1 by 2 delta x with second order accuracy. Okay, forward difference, backward difference, taking 2 points only, but these two are first order accuracy. Central difference I am getting at second order accuracy. Is it clear about it?
Yes, sir.
Okay. Because all these things you have learned, it is just recollecting the things. Okay, now if I want second order derivatives, what should I do? I have to take one more point. Okay, so if I want second order derivative with forward difference approximation, I have to take fi plus 2 also into consideration. Okay, so if you go back, so I have to consider this also. So if I use these two, fi is already there, fi plus 1, fi plus 2. Using this, I want to get f double dash I. So if I want f double dash, f dash should get cancelled. So I have to use these two. Okay, using algebraic manipulation, I have to see that f dash gets cancelled. So what should I do?
Multiply the equation 1 by 2.
Multiply the first equation by 2 and subtract it from here. So fi plus 2 minus 2 fi plus 1 is equal to, I'm going to get this 2 fi. Okay, this this is fi minus 2 fi. So I will get minus fi. So if I bring this side, it will become plus fi. Okay, and this gets cancelled. I am going to get dou square f by dou x square. So you can see here, second order derivative, forward difference, fi plus 2 minus 2 fi plus 1. One fi is there on the right hand side, that if I bring to this side, plus fi will be there by delta x whole square. And again, the terms that are neglected is from delta x whole cube, but I am dividing by delta x whole square. So it will become order of delta x. Okay, this is second order derivative with forward difference approximation. Okay, so if I want backward difference, I have to take fi minus 2. And again, if I do the manipulation, fi minus 2 fi minus 1 plus fi minus 2 by delta x whole square is order of delta x. And if I take central difference, okay, so if I take central difference, again, I take only 2 points, one on this side and one on that side and itself. So what I do is I add these two. I add these two. If I add these two, automatically these two gets cancelled. So fi plus 1 plus fi minus 1. Here, if I add 2 fi will be there. If I bring it to this side, I'm going to get dou square f by dou x square. And these two gets cancelled. So the neglected terms will be delta x to the power of 4 by delta x whole square. So order of delta x whole square will get. So this is the way. Central difference, fi plus 1 plus fi minus 1 minus 2 fi by delta x whole square. This is second order derivative with second order accuracy. So like this, I can get first order derivative, second order derivative, third order derivative. If I want third order derivative, you take fi plus 3. Then fi plus 1, fi plus 2, fi plus 3 are to be used in such a way that first order derivative, second order derivatives gets cancelled. then I get third order derivative. So like that, I have to go for higher order derivatives. I have to take one more point and then do the algebraic manipulation and get the expression for third order derivative, fourth order derivative, like that, either forward difference or backward difference or central difference. So the number of points needed for first order derivative is 2 points, second order derivative 3 points, third order derivative 4 points, like that. That you have to remember. Is everything okay till now?
Yes, sir.
Yes, sir.
Okay. And one more point here is, if I take first order derivative, okay, these things, you have seen that forward difference gives first order accuracy, backward difference gives first order accuracy, but central difference gives second order accuracy. So naturally, what we do is we prefer central difference so that I will get second order accuracy, higher accuracy. But based on the physics of the problem, right, sometimes you are forced not to take central difference, or you are forced to take only forward difference, or you are forced to take only backward difference, like that. So if I am forced to take only forward difference, I am having first order accuracy, but I want second order accuracy. Okay, how to get first order derivative forward difference with second order accuracy? So what I do for that is, so I have second order derivative forward difference with first order accuracy, and this particular term I will substitute in this expression. I got the expression for second order derivative forward difference. So this dou square f by dou x square, I substitute that equation here. So what happens now? From this term, this onwards, I am neglecting. And here I am dividing with delta x only, because dou f by dou x has delta x. I am going to divide with delta x. So the terms that are neglected is second order accuracy I will get. Am I clear about it? I take this equation, I try to substitute this expression dou square f by dou x square with already I have second order derivative forward difference. If I substitute here, I am not neglecting this. I neglect only this term onwards. Okay, and this is delta x whole cube. Now when I want to get dou f by dou x, I am going to divide by delta x only. And here what happens to this delta x whole square? Because I am substituting this expression dou square f by dou x square, here delta x whole square is there. This and that gets cancelled. Okay, so the neglected terms are second order terms. So it is second order accuracy. So I will show you that. Okay, here this is the expression fi plus 1, and dou square f by dou x square, which is fi minus 2 fi plus 1 plus fi plus 2. So this expression I substitute here. This expression here, you can see that. So I am going to get dou f by dou x as minus fi plus 2 plus 4 fi plus 1 minus 3 fi by 2 delta x. This is second order accuracy. You can see that it is first order derivative, it is second order accuracy, and it is using 3 terms. If I want, I told you first order derivative needs 2 points for first order accuracy only. If I want one more accuracy, additional accuracy, I need one more point. So here fi plus 1, fi plus 2 are taken, though it is first order derivative, to increase the order of accuracy. Is this clear?
Yes, sir.
So in this way, I can increase the order of accuracy. Suppose I want third order accuracy. Okay, normally we don't use it, but for exam purpose or some research purpose, you need third order accuracy. So first order derivative, if I want third order accuracy, what should I do? I have to substitute third order derivative with first order accuracy here, and second order derivative with second order accuracy here, so that I can get first order derivative with third order accuracy. So first I have to get these expressions, then I substitute here, and then I can get this for third order accuracy. So that is the way you can have higher order accuracy for the same derivative. So you should be in a position to derive the expressions for any order derivative with any order accuracy by having this particular logic. Okay, so I will show you some of the expressions. These are taken from, there is another book, I don't know whether I given you or not. There is a CFD book by 3 authors, Anderson, Tannehill, and Fletcher. Okay, I have written as Fletcher. I don't know whether I have sent it to you or not. Okay, but that is also one good book, 3 author book we call it as. So here these expressions are taken from that. Okay, so these are first derivative approximations with first order accuracy and second order accuracy, and forward difference, backward difference, central difference, everything. And this is taken 2 dimensions. That's why 2 suffixes are there. Ui plus 1. Here j will be constant. J will not change. Okay. So because dou u by dou x, I am taking derivative in the x direction. Y direction, it is same line. Okay. So j will not change. If I have 2 dimensions, then j also will change. That we will discuss later. Okay. Just forget about j here. Dou u by dou x at I is equal to fi plus 1 minus fi by h, like that. Delta x is h. Okay, so this is the way the expressions are given. And then 3-point second order derivative approximations. This also we have done already. And you can have finite difference approximations using more than 3 points. So that is third order derivative, fourth order derivative with central difference here, ui plus 2, ui plus 1, ui minus 1, ui minus 2. This is second order accuracy, central difference. And this is third order derivative, fourth order derivative. And then second order derivative and third order derivative for forward difference. You can see ui plus 3, I plus 2, I plus 1, I are used. Okay, so these are forward difference approximations for second order derivative and third order derivative with second order accuracy. So in that way, you can have the expressions. You should be able to derive these expressions. And one more important tip I will tell you, after deriving whether it is right or not, okay, one check we can make. The sum of all the coefficients is 0. The sum of all the coefficients will be 0. Suppose if I take this, okay, 2 minus 5 plus 4 minus 1. Okay, 5 minus 18 plus 24 minus 14 plus 3. If you see, it will be 0. And actually, what does it mean? Okay, so meaning of this expression is these are weightages. Okay, to get the third order derivative. Okay, so I have to use values at some 4 points, and each point contribution is this coefficient. Okay, so these 2 contribute more and these 2 contribute less. Okay, so these are like weight functions, like things. Okay, is this clear till now? Okay, there are so many expressions. Difference of program. Okay, here there is mixed derivative. And here, okay, I will show you the derivative. I don't know this. Yeah. So if I want dou square f by dou x dou y. Okay, so how to get this? I will write this as dou by dou x of dou f by dou y. Okay, and dou by dou x, it will be like, and what is dou f by dou y? If I take central difference, right? So both neighbors I have to take fi j plus 1 minus fi j minus 1 by 2 delta y. Central difference, first order derivative, I have to take the neighboring points fi plus 1 minus fi minus 1 by 2 delta x, right? So here, because dou f by dou y is there, 2 delta y will be there, and I have to take j plus 1, j minus 1. But in the y direction, I have to take the neighboring points. Is this clear?
Yes, sir.
Okay, now I have to substitute this here, dou by dou x of this. Okay, so dou by dou x of fij plus 1 and fij minus 1. Okay, what is dou by dou x of fij plus 1? If I want to central difference, j plus 1 will be same, but in x direction, I have to take I plus 1 and I minus 1. So you can see here fi plus 1 j plus 1 minus fi minus 1 j plus 1 by 2 delta x. This 2 delta y is taken out, and dou by dou x of fi j plus 1, it is written here. And dou by dou x of fi j minus 1, again j minus 1 will be constant. Fi will be written as fi plus 1 and fi minus 1 by 2 delta x. So if I expand this, I'm going to get fi plus 1 j plus 1 minus fi minus 1 j plus 1 f minus like this. All four neighboring four corners, if you draw it like a rectangle, all four corners I will get. I plus 1 j plus 1, I minus 1 j plus 1, I plus 1 j minus 1, I minus 1 j minus 1. This is like average of all the four. It's not average. Okay. Now, two corners are added and two corners are subtracted. Okay. I plus 1 j plus 1 and I minus 1 j minus 1, you will get positive. I minus 1 j plus 1 and I plus 1 j minus 1, you will get negative. Okay, by 4. Okay, this is the way I get. And if you want, you can change the order. I can write dou by dou y of dou f by dou x. And you are going to get the same expression. And this is for central difference. And this need not be central difference. It can be forward difference. If it is forward difference, then I have to write dou f by dou y in forward difference. And dou by dou x of, again, these two expressions I have to write with forward difference like that. Okay, so another way of using forward difference. If you dou square f by dou x dou by, I write dou by dou x of dou f by dou y. And dou f by dou y is fij plus 1 minus fij by delta y. So dou by dou x of fij plus 1, if I take fi plus 1 j plus 1 minus fij plus 1. Okay, this one. And dou by dou x of fij is fi plus 1j minus fij. Then I am going to get this. But these expressions will be different. Okay, for forward difference, backward difference, central difference, you will get different expressions. So why? Because, okay, as I told, sometimes I need forward difference, sometimes I need backward difference, sometimes I need central difference based on how the information is moving. Okay, if it is a diffusion term, like elliptic term or a diffusion term, all the information moves in all directions uniformly. So I always prefer central difference because every point depends on all its neighbors. But if it is convective domination, okay, so the flow is going like this. If it is going like this, every point here depends only on the point ahead of it, upstream of it. It will not depend on the point later to it. So the central difference will be failed at that time. I cannot take central difference. I have to take the difference based on how the flow is moving. If it is coming like this, I have to take point behind this. If flow is coming this, the point is to be taken after this. Okay, so from left to right, if it is going, the information, I have to take backward difference. From right to left, if it is going, I have to take forward difference. Am I clear about it?
Yes, sir.
Okay, so that is the way I have to decide what type of difference I have to take. Okay, this is the way I have to do Taylor series method. If I want to use polynomial method, okay, so this is another one, finite differences by polynomials. So how to do about it? Okay, again, okay, all these things now what I am doing, maybe I will take another one before going to polynomials. So I will take another case where the delta x may not be same. That is, it is not uniform grid, a non-uniform grid. I told you many times you will have non-uniform grid. It's still structured only. Okay, structured means I have to identify each grid point by the numbers of grid lines. Okay, then it is structured. But structured need not be, can be uniform or non-uniform grid. Means delta x can be same and delta y can be same, but sometimes it may be changing. The distance between the grid points may be changing. Because as I told, I need finer grid where the deviations are high and coarser grid when the deviations are not much. Suppose if I have a boundary layer like thing, So within the boundary layer, the gradients are high. So I need very close grid points. But away from the boundary layer, I can have coarse grid. So then the grid distance may be changing. I should not take coarse grid everywhere because accuracy is lost. I cannot take fine grid everywhere because the load on the number of grid points increase, the load on the computer increase. So I have to change the grid spacing. So there is one way of doing it is geometrical grid spacing. Okay, geometric series. Okay, first delta x I take, then some alpha delta x, right? So again, like that I increase. Okay, so if I will show you. Yeah, this is unequally spaced grid points. So if I take this as alpha delta x first, this is I plus 1, this is delta x distance, and I plus 2, it will have alpha delta x. Alpha can be more or less. If it is more than 1, it is increasing. If it is less than 1, the spacing will be decreasing. Okay, so this is alpha delta x, then it will be alpha square delta x, then alpha cube delta x, like that. So if I have that way, how to get the first order derivative, second order derivative, like that. Okay, so now if it is unequally spaced grid point, how to write the Taylor series expansion? Okay, fi plus 1 will be same. Fi plus 1 is equal to fi plus delta x f dash I, because delta x only the distance. This is clear, no problem. But if I want fi plus 2, okay, so this is f of x plus, what is the distance here? It is not 2 delta x. Delta x plus alpha delta x means 1 plus alpha into delta x. Is that clear? Is this clear?
Yes, sir.
So this is 1 plus alpha into delta x, and here 1 plus alpha whole square into delta x whole square, f double dash x, and 1 plus alpha whole cube delta x whole cube factorial 3, dou cube f by dou x cube. Like this I have to write. Okay, so once I write like this, first order derivative, same thing, because xi plus 1 delta x is the distance, it will not change. If I want dou square f by dou x square, okay, so what should I do? I have to see that dou f by dou x gets cancelled in these two expressions. And how to cancel dou f by dou x?
Should multiply with alpha.
Yeah, the first equation you have to multiply by 1 plus alpha, because here 1 plus alpha delta x, here delta x. So this minus 1 plus alpha into this, if I take, then dou f by dou x gets cancelled. So fi plus 2, this is fi plus 2 minus 1 plus alpha into fi plus 1, this one. Okay, and here fx minus 1 plus alpha into fx. So how much it will become? Minus alpha fx, and if I bring it to the left side, it will become alpha fi. So fi plus 2 minus 1 plus alpha fi plus 1 plus alpha fi is equal to, so how much I will get here? Dou f by dou x anyhow gets cancelled, and for dou square f by dou x square, here it will become 1 plus alpha whole square by 2 minus 1 plus alpha into delta x whole square by 2. So if I take LCM and join it, I am going to get 1 plus alpha into alpha delta x whole square by 2. Like this I will get. So I am interested in dou square f by dou x square. So take it to divide both sides by this. So dou square f by dou x square is fi plus 2 minus 1 plus alpha fi plus 1 plus alpha fi by this one, half into alpha into 1 plus alpha delta x whole square. Okay, so this is the second order derivative. But if I want first order derivative with second order approximation, what should I do? This dou square f by dou x square is to be substituted in this expression. And if I get dou f by dou x, okay, just some algebraic manipulation, you will get this. Minus fi plus 2 plus 1 plus alpha square fi plus 1 minus alpha into alpha plus 2 fi, like this. This is first order derivative with second order accuracy. If I want to check whether this is right or not, okay, so equal spacing, when it will be equal spacing? When alpha equal to 1, it will be equal spacing. So if you substitute alpha equal to 1 here, this should be same as the expression which we got for equal spacing. Is it clear?
Yes, sir.
Okay, so this is the way I have to use for unequally spaced grid points. Okay, you go through, there are many examples are given in the textbook. You go through the worked out examples. Okay, coming to the polynomials now. So in the polynomials, what should I do is, if I want second order derivative, I have to take 3 points, right? So 3 points means I have to fit a curve. 3 points, okay, that is 3 unknowns. I can have a quadratic equation. Okay, I cannot have cubic equation. If I want a cubic equation, I have to take one more point. Okay, so f of x is equal to ax square plus bx plus c if I take. So fi is, and here always take origin at xi. Take origin at xi. And xi plus 1 then at a distance of delta x, and xi plus 2 at a distance of 2 delta x, like that. Okay, so fi is axi square plus bxi plus c. And what is xi? Xi is 0. I have to get a, b, c. I have to get this curve. So to get the curve, I have to know the values of the constants a, b, c. And I know the values fi plus 1, fi plus 2, because I know the function values, right? So fi is equal to axi square plus bxi plus c. And xi is 0 here, right? So this is 0, this is 0, c. So c value constant is equal to fi, because already I know fi plus 1, c a constant is known. Now fi plus 1 is equal to, substitute here I plus 1, a xi plus 1 whole square and b xi plus 1 plus c. And c is already fi, you can substitute here. Okay, and what is xi plus 1? Xi plus 1 is delta x. So substitute delta x. So a into delta x whole square plus b into delta x plus c is equal to fi plus 1. C is already known, fi. So if you substitute here, I am going to get fi plus 1 minus fi as a delta x whole square plus b delta x. Okay, now fi plus 2. A into xi plus 2 whole square, and this is 2 delta x. So a into 2 delta x whole square plus b into 2 delta x plus c. Okay, so this is again fi. If I take it this side, fi will be there. And I am going to get two equations. One is a into delta x whole square plus b into delta x is equal to fi plus 1 minus fi. And a into 2 delta x whole square plus b into 2 delta x is equal to fi plus 2 minus fi. So these two equations are to be solved for a and b. So if you solve a and b, I'm going to get a something here and b is here, c is already fi. Okay, so once I get a, b, c, now what I am interested in? I am interested in the derivatives. And what is f dash x here? Differentiate this. I'm going to get 2ax.
2ax plus b.
So 2ax plus b, and when I want derivative at this point, right? So xi is 0. So 2axi that goes off, and you will get. So b value is nothing but the derivative. Okay, so this is dou f by dou x at I is b, and dou f by dou x is 2x plus b, and dou f by dou x at I is b. So dou f by dou b is already known, so this is nothing but you substitute here. This is dou f by dou x. And what is dou square f by dou x square? Again, differentiate this. I am going to get 2a, and a is already known, so this is the expression for second order derivative. So you can get second order derivative with first order accuracy, and first order derivative with second order accuracy you will get at a time. Okay, this is the way I can get. Suppose if I take one more point, fi plus 3, then it will become ax cube plus bx square plus cx plus d, like that. And if I solve a, b, c, d, then I am going to get third order derivative with first order accuracy, second order derivative with second order accuracy, first order derivative with third order accuracy. All of them I can get by solving them. But only thing is I have to solve. D will be known directly fi, but three equations a, b, c are to be solved using is a Cramer's rule or something. You have to solve the matrix. A, B, C are to be solved. 3 equations will be there, A, B, C unknowns you have to solve. So it is a little bit mathematically involved. But you will get first order derivative with third order accuracy, second order derivative with second order accuracy, and third order derivative with first order accuracy at a time. So that is the way I can go for polynomials. In the same way, I can do for unequally spaced differences also. Here you can take delta x, you take it as alpha delta x, and I can do in the same way. And so that is the way, this is unequally spaced grid points. So fi plus 1 is a delta x whole square plus b delta x plus c. Fi plus 2 is a 1 plus alpha whole square delta x whole square and plus b 1 plus alpha delta x plus c. Okay, so again, if because xi is 0, so fi is c, and fi plus 1 I like this, and I have to solve these two for ab. C is fi substitute, take it this side, and these two are to be solved to get a and b. So a and b are obtained, and in the same way as I have done previously, dou f by dou x dou square f by dou x square I can get here. So these expressions also you can check whether it is Taylor series expansion or polynomial expansion, you are going to get the same expressions. Again, if you put alpha equal to 1, you are going to get for equally spaced points. All these things you can check. And another check I told, if you sum all the coefficients, the sum of the coefficients must be 0. So these are the different checks you can make whether to know whether your expression is right or not. Is everything okay?
Yes, sir.
Okay. Okay, up to that, we'll stop here. So we have discussed about the discretization of partial differential equation in 3 methods: finite difference, finite volume, and finite element methods. And finite difference methods are differential methods, and finite volume and finite integral are integral approaches. And that is more fundamental equation. But the finite difference method is the easiest one, very simple one. And it is restricted to structured grids only. And the finite volume and finite element method can be any unstructured grid. So the domains must be simple rectangle for finite difference, any complex domains for finite volume and finite element. Coming to finite volume and finite element are successful for the structural problems because the equations are linear. But usually we prefer finite volume methods for nonlinear equations. So one is nonlinear. Another thing is I can use iterative methods for solving the matrices, but their direct methods are used where round of error is large. So those two are the limitations for finite element. So finite volume is the most popular and widely used in the commercial packages. So that is up to that. So coming to finite difference methods, we can discretize it using 2 methods: Taylor series expansion or polynomial expansion. So if you take Taylor series expansion, Taylor series are normally used to find out the values of the function at neighboring points, knowing the function and derivatives at a particular point. But here, discretization here what we do is we try to get the derivatives knowing the function at all the points. So we have seen how to get the derivatives. If for first order derivative you need 2 points, second order derivative 3 points, third order derivative 4 points, like that. And then I should be able to get any order derivative like that. So if you want to increase the order of accuracy, I have to substitute the higher order derivatives with lower order accuracy into that. If I want first order derivative with third order accuracy, I have to substitute there third order derivative with first order accuracy, second order derivative with second order accuracy. Then I can get first order derivative with third order accuracy. So like that, I should be able to get any order derivative with any order accuracy. And we have seen how to use it for unequally spaced points. And also we have seen how to get for mixed derivative, like dou s square f by dou x dou y. So it can be again central difference, forward difference, or backward difference. And then we have seen how to use the polynomial expansion to get the derivatives. And again, you can get based on what derivative you want. If you want second order derivative, take 3 points, third order derivative 4 points, like that. And while getting the second order derivative with first order accuracy, you can get first order derivative with second order accuracy. So those expressions, it is like a byproduct. You will get another one also. In that way, I can solve or get the finite difference form of partial differential equation. Okay, so we have seen forward difference approximation, backward difference approximation, central difference approximation. And based on the physics, I have to see which is suitable for which type of expression. Time derivative, suppose. I cannot take central difference there. If I want to get the time derivative at this point, I can use only past value. I cannot use the future value. Future value is not there. So it is always using previous point. I have to calculate the next point. Okay, using the previous and present, I have to calculate the future. It is one-sided difference. But if it is diffusion type, I can use the central difference. So what I want to stress here is I have to understand the physics of the problem to understand what type of differences I have to take for the equation. Okay.
Yes, sir.
So I'll stop here. Shall we go for the story then? Okay, here one interesting story. This all of you are popular hare and tortoise story, but this is a very old one. My fathers and forefathers have studied it, but now based on the present scenario, people wanted to develop it further. So this is a management lesson. So in management MBA class, these type of stories they will tell. Okay. So actually, everyone throughout the world has kept giving the example of tortoise, saying that slow and steady wins the race, and emphasizing the value of persistence and dedication. Well, no one has ever bothered to ask the hare his side of the story. So let me tell you the story from a different point of view. So I met the hare and sat down with him for a heart-to-heart talk. This is what he had to say after he spent the better part of a balmy summer afternoon getting to know one another. It was a wonderful experience, believe me. Yes, I am the hare who lost. No, I did not get lazy or complacent. Let me explain. I was hopping over the meadows near the hills and looked back to realize that the tortoise was nowhere to be seen. Assured of my healthy lead, I decided to take a short nap under the large banyan tree near the pond. The anticipation of the race had kept me up all night. So for days, that old silly tortoise had boasted about his ability to plod for hundreds of miles without stopping. Life is a marathon, he said, not a sprint. I wanted to show him that I could run both far and fast. The shade of the tree was like an umbrella. So I found an almost oval rock, covered it with grass, and turned it into a makeshift pillow. I could hear the leaves rustling and the bees buzzing. It felt they were collaborating and even conspiring to put me to sleep. And it didn't take them long to succeed. I saw myself drifting on a log in a beautiful stream of water. As I came near the shore, I found an old man with a flowing beard sitting on a rock in a meditative pose. He opened his eyes, gave me an all knowing smile, and asked, "Who are you?" "I am a hare. I am running a race." "Why?" "To prove to all the creatures in the jungle that I am the fastest." "Why do you want to prove that you are the fastest?" "So that I get a medal, which will give me status, which will give me money, which will get me food." "There is already so much food around." He pointed to the forest in the distance. "Look at all those trees laden with fruits and nuts, all those leafy branches." "I also want respect. I want to be remembered as the fastest hare who ever lived." "Do you know the name of the fastest deer or the largest elephant or the strongest lion who lived 1,000 years before you?" "No." "Today you have been challenged by a tortoise. Tomorrow it will be a snake. Then it will be a zebra. Will you keep racing all your life to prove that you are the fastest?" I didn't think about it. I don't want to race all my life." "What do you want to do?" "I want to sleep under a banyan tree on a makeshift pillow while the leaves rustling and the bees buzz. I want to hop over the meadows near the hills and swim in the pond." "You can do all these things this very moment. Forget the race. You are here today, but you will be gone tomorrow. I woke up from my sleep. The ducks in the pond looked happy. I jumped into the pond, startling them for a moment. They looked at me quizzically. Weren't you supposed to be racing with the tortoise today? It's pointless, an exercise in futility. All I want to be here. Hopefully, someday, someone will tell you the world my story. That I lost the race, but got back my life. Okay, it is a philosophical story. Actually, I thought there is another story also. And next week, I will tell about that story, which is management story. But this is philosophical story. So we are all in the rat race, forgetting they enjoy this moment. Okay, so that's what it wanted to stress. Live life to the fullest today, tomorrow, and always. Start the life with new perceptions. Thank you. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.